Good morning, Astronomy 1010. Welcome to part 2 of lecture 4. Last class, we learned about Newton's laws of motion and other basic physics concepts. Today, all things gravity. Today, we're going to be doing a homework from chapter 4, and it's a pretty difficult one. So it's going to involve a little bit more crunchy math than we're used to. The thing I want to tell you is if you're one of the few students who insists on typing up your homework, don't do that. Not this time. Last time I had to penalize a few people because they just could not format it the way I wanted them to. They were still trying to write out p squared, like the word squared, equals a cubed. We can't do math like that. I can't grade math like that. If you haven't figured out how to use your equation editor and make it look real good, then you should just write it with pencil and paper and take a photo of it. It's so easy. Paper's cheap, pencils are cheap, and it's a foolproof way to not piss me off. Okay, so please consider that, all right? Okay, let's start by talking about Woolsthorpe Manor. Isaac Newton's ancestral home still exists today. And if you type Woolsthorpe into the internet, the very first thing that comes up is a picture of his ancestral home. And you'll notice that in the foreground, you can see an apple tree. This is significant because Newton had wrote in his diary that one day he was occasioned by the fall of an apple. So he was staring out the window and he saw an apple fall from the tree to the ground. And he said, "This left a deep impression on me. I realized that the same force that pulled that apple to the ground must be the same as the force that held the moon in its orbit. Because remember, the moon travels in roughly a circle around the Earth. According to Newton's law of inertia, let's get an annotate arrow here. An object in motion should stay in motion unless acted upon by an outside force. So if the moon was temporarily where my red dot is, its direction of motion is currently to the right. And according to Newton's law of inertia, it should want to continue to move towards the right, unless acted upon by an outside force. But where was the outside force? Well, wherever that outside force was, a few moments later, the moon has moved to a new position over here, and now its direction of motion was like that. And a few moments after that, the moon has moved over here with its direction of motion in the direction of the black arrow. Where could the force be? Well, Newton realized that if the same force were to tug on the moon that tugged on the apple, the force would always be directed towards Earth, and that the moon's motion would be the combination of its sideways velocity and its downwards acceleration, should we say. And so its resultant motion would be a product of the two, and it would move along the circle. Then it would continue to have a sideways motion because no force is acted tangential to the circle, but the downward force would produce more motion along the path. In other words, the same forces that worked on Earth to make stones roll down a hill were the same forces holding the planets in their orbit. And that was a profound realization because remember that Aristotelian ideas and Platonic ideas that the heavens were somehow separate from the Earth have percolated down to us throughout the ages, even into modern Christianity, where people imagine heaven as being this kind of cotton candy palace with angels and clouds and everything is great and nobody feels bad and it's like freedom forever, whereas Earth is like nasty, brutish, and short. In reality, the same forces govern the heavens and the Earth. They're all part of the same system. Now, it's a little bit elaborate to get into how he derived his equation for gravity. I will refer you to the Principia Mathematica for further details. But what we do know is that he eventually came up with a primitive version of the gravitational formula today. And in the interest of time, that's where we're going to start out with. So let's take a look at this. Share screen. Okay. I want to jump ahead to the.
I have a question, if that's
Okay.
okay.
Yeah, sure. Hit me.
In the previous picture, it was like orange and the circle. It's
Yeah,
not necessarily like a 90-degree angle, is it? Or is it?
it is a 90-degree
Because
angle.
like the way it's, so would the like the movement or like the direction be be in the middle, or is that like part of the equation where it's like not necessarily like
Uh, uh,
45 degrees?
well, the equation that we're about to learn is for the force of gravity. So the equation
Oh,
that
okay.
we're going to learn, all that does for us, that's one part of it, is, all right, so
Mhm.
let's put the moon right here where the red circle is. The equation that we are about to study will tell us the magnitude of the force between the Earth and the moon. I drew two arrows, but it's really just one force. So let's get rid of that most previous arrow. The equation that we just are about to learn is going to tell us the direction of the force. Once you know the force, Nori, you can then use the equations of motion to determine the trajectory. And the question that you were trying to ask is, how does this arrow sideways plus this force downwards contribute to its motion? You can see that if you tug sideways and you tug down, the resulting motion is going to be like kind of somewhere in between the two, right?
Mhm.
It turns out that the proper velocity to have is one in which your velocity is a little bit sideways, and then you have a potent downward acceleration. Well, I don't know. You got to mix and match them just the right way, such that its motion will kind of be a product of the two, and the Earth will move over there. Then it will continue to have sideways velocity, but it will have a new downwards direction. And so the traveling along the circle is the constant sum of the sideways velocity and the downwards acceleration. Now, to analyze that problem, that takes a little bit more math. We won't have time for all that today, but we won't need to,
That's
because
okay.
if we calculate the force of gravity, we then know that it's going to move on an ellipse or a circular orbit, a la Kepler's laws. I'll get to that part of it next. You'll see. For now, we have some new things to teach you guys. Let me go back to that slideshow. Sorry, I was trying to show you guys, what was that number? 46. So this is going to be our most generic setup for the equation for the law of gravitation. And eventually our law of gravitation is going to look just like this formula. But I want to slow our moves down for a second. Before I get to this, I want to just meditate on the setup. Newton realized that the essence of gravity had to do with the masses of the two objects, that it was mass itself which was somehow causing the gravity. And so in the most generic setup, any two masses, any two objects with mass, they could be two planets or a planet and a moon. They could be two bowling balls. They could be a marker and an eraser. Technically, those have mass. Any two objects with mass are then separated by a center-to-center distance. And it's important that you remember it's center-to-center distance, which we call little d. So let's write this law the way Newton wrote it in his Principia. Let's focus on me. Okay. Introducing the law of gravitation. So our setup is two masses, one which is called M1, the other called M2. They are separated by a center-to-center distance, little d. When Newton wrote his law of gravitation, he wrote it in the following manner. The force of gravity, he writes, will be proportional to the product of the two masses and inversely proportional to the square of the distance between them, where I have introduced a new mathematical operator. This little Jesus fish means proportional to, and we should probably talk to you guys about that. Proportional to is not this. All right, I need to fix my glare. Guys, copy that down and give me 1 second. I need iced tea. The coffee is driving me out. All right. Sorry about that, but this mathematics is thirsty business here. Of the 4 people showing screens with me, or of the 2 people that I can actually see, how many of you have seen a proportionality symbol before? Awesome. Okay. That's what I was afraid of. So we need to talk about that. Click the tab with your, oh, okay. Sorry. Okay, proportional to, boy, I didn't really help with the glare that much, did I? It's the sort of the same thing as it varies as. So what this means here is it means you can't actually calculate the force in newtons, but you can tell how the force will change if you change one or more of the quantities here. This is telling me that gravity depends upon 3 things: the first mass, the second mass, and how far apart they are between them. But it also depends upon these things in different ways. If the force is directly proportional to the product of the masses, in other words, if the masses are on the top of the equation, that means more mass will equal more force. If the distance is on the bottom of the equation, that means greater distance is less force. The square means the force falls off quite rapidly with distance. It falls off exponentially. What you're supposed to do with the proportionality sign is you're supposed to use it to figure out, if I change some of these quantities, how will the force vary? Let's try it together. Suppose, for instance, I had Earth and the moon and the distance between Earth and the moon, and I could suddenly take the moon and make it 2 times farther away. So the question I want to ask is, if the moon were 2 times farther away, if the moon were 2 times further away, how would the force of gravity change? To answer that question, I would recognize that we're not changing the mass of Earth or the moon. We're only changing the distance. So I would rewrite the proportionality symbol as the force of gravity is proportional to 1 over the distance squared. And that means the force of gravity here is only going to vary as the distance varies. And then I would substitute in for the distance a factor of 2. In other words, the distance is varying by a factor of 2. So the force is going to change by a factor of 1 over 2 squared. 1 over 2 squared is 1/4. And thus, I have learned that the new force is 1/4 the original force. And another way to write that, of course, would be 4 times weaker. That's what that means. The force of gravity would be 4 times weaker if I moved the moon to twice its current distance. I think this is an old marker. Oh, yeah. This is the good marker that I want. Do you guys have that? I'm going to erase. Okay. Now it's your turn to prove to me that you understood what I just did there, because this is going to be one of our first homework assignments. Suppose I double both masses. Can you guys tell me how the force of gravity would change if I double both the masses simultaneously?
I have a question.
Sure. Ask away.
I'm sorry. How did you like decide that one is gonna, like in the last problem it was F? What would you call this one again? You said a Jesus fish?
Yeah, proportionality symbol. It's a proportionality operator.
That like the proportionality symbol, and then you did 1 over d squared. How
Right.
did you get the 1 if it's like m1 times m2? Like I didn't really understand like how you just put 1 there.
You're asking the right questions here. The reason why I replaced this with 1 is because in the previous question, I didn't alter the masses at all. You might have missed that setup there. What I said in the previous question was, suppose I took my 2 masses and I just doubled the distance between them. In that case,
Oh, you didn't like mess with the mass. Okay.
I didn't mess with the mass.
You just moved it.
So I didn't need to include the mass. See, proportionality symbol is a different kind of operator than equals. With an equals, you actually plug numbers in for everything and you get a force 25 newtons or something, right? Here, you don't do the same thing. The proportionality symbol is which of these are varying, I'll tell you how the force changes. And if you don't vary the masses, you're essentially varying them by a factor of 1.
So if you moved the mass, if you like changed the mass, but you didn't like move like where they were.
Well, we don't say move the mass because that's a distance thing. We say change the mass, right?
Okay.
So that's the exact question I'm asking you now, Nori, and maybe you can try it to see if you get it. Suppose I double the masses, but I don't touch the distance. Let's first write it out symbolically. The force now will be proportional to what? What do I write in terms of my variables?
2m. 2 times m.
No, what I want to do is I just want to write it symbolically before I try putting in. See, when you say 2, I think you're trying to substitute in double. I don't want you to do that yet. I want you to go even slower. I just want you to rewrite the equation, keeping only the variables that are changing. So try it again. Does anyone understand me?
Isn't it m1 times m2?
Thank you, Kim. That's what I wanted to hear. And what this says mathematically is it says the force is directly proportional to the product of the masses. Okay? And that's what I wanted you to do first, just to recognize that distance doesn't change, but the masses keep their relationship. And this is actually how Newton wrote it in the Principia. The force is directly proportional to the product of the masses.
And could we write that over 1 being the distant, because that doesn't change?
Sure.
Like,
If you want to
yeah.
do that, then you better do 1 squared. You can't ignore the square if you're going to play that game.
Gotcha.
In this case,
Okay.
1 squared is 1, so it doesn't really matter. Okay, fine. If you want to put it that way, you can. Now I write another proportionality, and now you substitute the factor by which the masses change. So what should I write next?
So it should be 2 times 2 over 1 squared.
Let's ignore the 1. 1 squared is 1. Anything over 1
Okay.
is itself. So let's just reduce it to 2 times 2. Now, because we have an actual product of numbers, we can transform this from a proportionality to a hard equals, because we can actually compute that. And the answer is,
4.
and what's the meaning of the 4?
It's 4 times stronger. The gravitational force is 4 times stronger.
All right, you guys are getting me here. This is good. The new force is 4 times stronger. Excellent. Now listen, the first time you learned about Mr. Jesus Fish here, it doesn't really seem that impressive to you. But I want to warn you against taking this for granted or thinking this is stupid. This is not stupid. This is a powerful mathematical operator that professional scientists use all the time to quickly analyze and interpret mathematical equations. If you know how to wield this Ginsu knife, you can very quickly analyze math problems and see how they work and see what will happen. And I will be showing you sneaky examples of this along the way. There's a reason why I'm incorporating this into my astronomy lesson. This is a technique that professional scientists use to get deep insight into math problems. Okay, now that you've had an introduction to the proportionality argument, let me erase this and let me talk about why this is as far as Newton had gotten. I'm erasing. As I mentioned, if you were to pick up the Principia Mathematica, actually, it's kind of ironic how I started off this class. Remember how I started off this class complaining about people who write out their homeworks in Microsoft Word and they write their math as force is proportional to, well, that's actually how Newton writes it in the Principia Mathematica. So those students are actually following in some footsteps of giants here. But no, don't do that. You're not Isaac Newton yet. Okay, so he just writes out in words the way my irritating students do. The force is proportional to the product of the two masses and inversely proportional to the distance squared. And because of this, we credit Newton with the discovery of the law of gravitation. However, let's think about the units that we measure these quantities in, especially within the MKS system. In the MKS system, what units do we use to measure mass?
Kilograms?
That's right. In the MKS system of units, which I described last time, what units do we measure distance in?
Meters.
Excellent. In the MKS system of units, what do we measure forces in?
Is it meters over seconds squared?
That's acceleration.
Acceleration, okay.
Newton.
Newtons. And by the way, for memory's sake, Newtons are kilogram meters per second squared. It's mass times acceleration, right? Okay. Now I need you to stop and think. Newton may have discovered the law of gravitation, but Newton did not invent gravity. Gravity was invented by nature herself. For instance, we invented the kilogram. Human beings decided that this should be a good reference mass, and this nugget, which is about half a brick, should be the quantity that we measure masses in. We imposed this idea on nature. Likewise with the meter. We decided that 1 meter would be an appropriate length to measure out the universe in, and we imposed our idea of the meter onto nature. And that means in a way that we invented the Newton, because if we invented kilograms, meters, and seconds, we decided that 1 Newton would be a standard unit of push. But we did not invent gravity. At some point, we actually have to ask nature for her opinion about how gravity works. In other words, what we have to say to nature is, if you had 2 1-kilogram masses separated by 1 meter, how strongly would you plan on tugging on those 2 masses? We have to perform some kind of experiment. Newton could not figure out how to turn this into an equal sign because he had no way of measuring gravity. And one of the reasons why is gravity is actually a stupidly weak force. For instance, these 2 little bouncy balls that I got from the Museum of Science, these moon balls, they have mass, albeit a very small mass. And if I hold them some distance apart, like 30 centimeters, 2 masses, a distance between them, there should be a force of gravity between these 2 bouncy balls. But I can't feel it. I don't feel any force at all. That's because gravity is a weak-ass force that isn't potent enough for you to... There is a force there, but it's so microscopic that I can't even tell it from the wind. In fact, really, gravity is so massive that you don't even start to notice it exists until you build up a whole planet's worth of rock and metal. And then suddenly you realize, oh, damn it, I'm actually stuck to this thing, and other things that I drop stick to it as well. That's kind of funny, right? The person who figured out how to turn this into an equal sign was a different scientist, one you've probably never heard about, but I'll share with you. His name was Henry Cavendish, and he performed this legendary Cavendish experiment. I don't know what the Cavendish banana is, but the Cavendish experiment was kind of cool because he basically, all right, let me try to show you the setup here. Maybe this could be the best photograph. It's just amazing that it even worked. But he took these huge, large spheres of lead, probably about the diameter of a bowling ball, and he put these bowling balls on a kind of beam separated by some fixed distance. And then he suspended some smaller lead spheres here and here. He connected them by a very thin rod, and he dangled the thin rod from what we call a torsional fiber pendulum. That is a very thin wire of metal which could freely swing back and forth. Now, because the mini balls were sort of suspended from this thin wire, the wire could actually rotate and deflect, and he actually got gravity, or gravity was actually strong enough to pull these things by a microscopic amount. Even though it was tough to see the amount that they were deflected by, he was able to measure it by means of a clever strategy. He put a mirror onto the torsional fiber and then bounced a light source off the mirror. And as the mirror rotated by a very tiny angle, the deflection of the beam was actually quite large if you watched it on a wall far away. So we basically used the small angle formula to kind of turn this small deflection into a large angle on the wall far away. Just an ingenious experiment. When he originally did this, he was able to calculate the magnitude of the force between these 2 spheres. And ironically, he wasn't interested in improving this formula. He was interested in making the first ever estimate of the mass of Earth. So weirdly, when he published the paper in 1870 something or whenever it was, he wrote the paper up to the Physical Society as on a new method of estimating the mass of Earth, as if that was what was the most important part of his experiment. And at the time, it was certainly interesting. But what was really fascinating was he had calculated a constant of nature, an index of the strength of gravity. And today we call it big G. I'm going to put it out in front of the equation. And if you include big G, then you can put an equal sign here, because now plugging these values in will actually give you the strength of the force. So I've introduced a constant of nature known as the universal gravitational constant. And it gets its own letter, big G, and it has a value of 7 times 10 to the negative 11th power, and the units are meters cubed per kilogram per second squared. Okay, just hold on for a second here and let's think about this. For those of you who are not steeped in the lore of physics, a constant of nature is a number which we can measure, but is tuned into the construction of the universe itself. Even though we have a letter to represent it, this number will never change. It's the same for 2 planets, for 2 galaxies. It's the same for 2 ping pong balls. It's always the same. And what you can think of big G as, you can think of it as an index of the strength of gravity. In other words, this number tells you how strong gravity is. Because it's a 7 times 10 to the negative 11, that means gravity is a weak-ass force that, you know, isn't very strong for everyday ordinary-sized objects. Don't confuse big G, the universal gravitational constant, with little g. Little g, what is little g? Can you guys remember? How's your memory cells? What's that little g all about?
It's Earth's gravity.
Don't say Earth's gravity. That's not the best way to say that.
The local acceleration of Earth's gravity.
I think an acceleration is different than gravity itself. It's the acceleration due to Earth's gravity. The words matter here, Jenna. So, but yes, you got it. And that has a value of 10 meters per second squared. Not the same thing. Okay, I think at this point we got to try it to understand it. So let's take our first assignment here. This is going to be a sample problem, a la the type you'll have to do in your exam. By the way, I'd like to mention, if you haven't thought about this week, there's next week, and then there's the exam. It's a coming. Time to punch into our calculators and train, okay? Our goal today to start with is for us to compute the force of gravity between Earth and the moon and find out how many newtons are holding these objects together. I'm erasing. Okay. This could easily be a problem on your midterm exam. Let's see how we handle it. Find the force of gravity between Earth and the moon. To solve this problem, you're going to need some givens. Given the following quantities. The mass of Earth has been measured by Henry Cavendish to be 6 times 10 to the 24. This is going to get a little messy, kids, so I'm going to use red for units. Kilograms. The mass of the moon was measured by somebody else. Sorry. Somebody loves me. All right, there we go. The mass of the moon is 7 times 10 to the 22 kilograms. And the distance between the Earth and the Moon is 384,000 kilometers. What should I do, students?
Plug it into the formula.
We can't do that right away. Sorry, whoever said that, Jenna. Jenna, there's something we need to do first. See, Jenna, every formula is like a little monster. You got to feed the little monster what it wants to eat. Nori's cat there, Willow, she doesn't feed her cat dog food. That would be messed up, right? And you wouldn't feed your dog cat food. That would also be messed up. Likewise, a formula is like a little monster, and it wants to eat certain things. In our law of gravitation, F equals big G times M1 times M2 over the distance squared. This formula only works for MKS units. So does that tell you what we have to do first, Jenna?
Yeah, we have to convert the distance to meters.
Yeah. K stands for kilograms, M stands for meters. These are not meters. All right, so that shouldn't be too hard for experts like you guys in dimensional analysis. So let's first convert the distance to meters. How do I do that?
We use the conversion factor of 1 kilometer equals 1,000 meters.
Okay, sure. I like your theoretical description. Now just tell me how to do it. Walk me through it. In other words, Jenna, I want you to apply the 4 steps of dimensional analysis.
Okay. Someone might have to help me. I'm kind of forget. Like,
No,
it
Jenna,
takes-
come on. Jenna, you know this. Listen, Jenna, do you have your notebook? You're in class every damn day. Could you just open your notebook to the 4 steps of dimensional analysis and we'll read them together? This can be a group project.
Okay, so we'll write down the number to convert with its units.
All right, so what do I write down?
So 384,000 kilometers.
Good. That's step 1. We just write the number we're going to convert down. What is step 2?
We multiply by a division bar.
Okay, that wasn't so bad. What's step 3?
We put in the units to be canceled.
We put in both units, one of which is to be canceled. So anyways, what units do I put in?
Kilometers on the bottom, meters on top.
Okay, that's step 3.
And then we put the numbers in second using our conversion factor.
All right, so tell me how to do that. Sounded like you had a good conversion factor earlier.
Yep, so it's 1 on top and 1,000 on the bottom. Oh, wait, sorry, the opposite. 1,000 on top.
1,000 meters are equal to 1 kilometer, right? Okay, now Jenna, you're so good, I bet you could do this without even a calculator. No, don't look at your calculator. You're missing the point. Let's just think about this. How many zeros do you have there?
3,
How many zeros do you have there?
3,
For a grand total of how many zeros?
6.
So what if we wrote this in scientific notation, but did it in a kind of cute way? What if we just carry over the 384, and then we'll just make it times 10 to the 6, because there's 6 zeros. Now that might not be proper form of scientific notation, but it's valid. 384 million meters. That's a kind of, you can put right into your calculator that way. Okay, now we are ready to punch this all into the formula, but we're going to write it out first. Do you guys have that copied down? Because I need to take some board space back. All right. So I'm going to replace this up here with 384 million meters. So I don't forget. And now I'm going to clear this out. All right, let's set it up as follows. The force of gravity between the Earth and the moon. I'm going to need a big division bar because there's going to be a lot in here. First, we'll put in big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times the mass of the Earth, 6 times 10 to the 24 kilograms, times the mass of the moon, 7 times 10 to the 22 kilograms. And I want you to notice how I'm going to write the distance in the bottom. Divided by 384 million meters. And I'm actually going to put parentheses around it, and then I'm going to square it. Now, I know for a fact that no one is going to listen to me here, but I'm going to say it anyways, just to heat the air in my apartment up a little bit, okay? These parentheses are not for your calculator. The parentheses are there because the square is being distributed to both the number and to the units. So these parentheses are for unit note bookkeeping, okay? Write all that down, and then I'm going to teach you how to punch this in. Nori, give me a thumbs up when you're good to go. Jenna, give me a thumbs up when you're good to go. All right. Everyone take out your calculators. I mean, everyone, including those of you who are watching later on. Okay. Ready? Punch with me. 7 exp negative 11. Times 6 exp 24 times 7 exp 22 divided by 384 exp6. Now we have to square that, square key, and then we hit equals. Everyone hold this up to the screen so that I know you did it right. Hold on, keep them there. Good Valentina, good Nori. Ian, hold on. Good Ian. What about Kim and Jenna? I'm looking for you guys.
I messed up.
How'd you mess up?
The very first step, I couldn't find the negative key.
Oh.
Where's
Kim, what happened to you?
I mistyped.
Okay. So this second, let's try it a little faster. The negative key is there above the 7.
Okay, yeah, that's
If
what
I go full speed, you're not going to like it. 7 exp negative 11 times 6 exp 24 times 7 exp 22 divided by 384 exp6 squared equals. That's not even full speed. Okay. One day you'll get this fast. Okay, don't erase it. How do I write my answer? Valentina. What do you think I should write down, Valentina?
I knew you were gonna say my name.
You could feel
I don't know why. I was like, I have no idea how to say this, and he's gonna say my name.
maybe that's why I picked you. I could sense your hesitation, and I, like a wild animal, I pounced on your fear. Okay, so Valentina, we have to do some good rounding. Let's round the number really, really hard. What do you want to round?
Can we round it to 2?
Yes, bold. I like your bold moves, Sarah.
So it will be 2 times 10 to the 20.
Beautiful. That's exactly what I wanted you to do. But here's the bigger issue now, Valentina. You've rounded the number. You've rounded good. I'm proud of you. But what are your units? A little bit lower. What do you think your units are? The way this game
Newtons.
works.
Can they be newtons?
Yes, they have to be newtons because this is a force. They can be newtons, they have to be newtons. So very good. That is one way to reason, Valentina. The way that you reasoned there was perfectly acceptable. And I want you to all pay attention to how her reasoning went. She went, well, I don't know about all this crazy shit because I don't understand all that, but I know this is a force. And Brendan taught me that forces are measured in newtons, so those have to be newtons. And you are correct. There's also another way to do this, Valentina. You can do it by using dimensional analysis to cancel out your units. For instance, this square will also square the meters. And meters squared kills 2 of the meters and leaves a single meter behind. This kilogram cancels with that kilogram, leaving a single kilogram behind. And there's still the case of 1/second squared. So the final units are kilograms times meters per second squared. And so it turns out to be the same thing as a Newton. Now you could do it that way where you reason by canceling out units. That's one method. Or the other method you could do is to use your intuition and say, well, what units should a force be in? They should be in newtons. Either method is okay.
Sorry if this is kind of an ignorant question. Again, I do have to do labs after this class, but how did you get from meters squared to second squared?
I didn't get from meters squared to second squared.
I just mean like where did
Do you see this little S with a 2 on it?
Oh yeah, totally. Yep. Okay.
I just kept that. I didn't throw it away. That's all I did.
Okay.
Does that make sense now?
Yeah, definitely.
And by the way, there were no meters squared. This was a meter squared. That was a meter cubed. And you understand what that means, right? A meter cubed means a meter times a meter times a meter.
Yeah, like three-dimensional
space. Meter squared means a meter times a meter. So I cancel out 2 of the meters and 1 meter is left over, correct?
Okay. Yep.
Okay.
Thank you.
All right. Okay. So that's the force of gravity between Earth and the moon. Put a box around it. And I liked Valentina's rounding. She did very good. All right, now listen. We have to try this again because I want to see if you guys can do it without the training wheels, okay? What do you guys suppose is stronger, the force of gravity between Earth and moon or the force of gravity between the Earth and sun? What does your intuition tell you?
I want to say Earth and the moon because the moon is much closer to Earth.
Okay. Well, why don't we find out? Let's calculate the force of gravity between Earth and the sun next. That will be a good test to see if you can do this with less help from me. I'm going to erase. Do you have it all? Here it goes. All right. New question. Calculate force of gravity between the Earth and the sun. Given the mass of Earth is still 6 times 10 to the 24 kilograms. The mass of the sun is 2 times 10 to the 30 kilograms. And you guys know the distance. The distance between them is 1 AU. 1 AU is 150 million meters. I'm sorry, whoa. 150 million kilometers. Apologies. What's my first step?
Convert the kilometers to meters.
That's right. Jenna, you've already successfully done that once. Ian, it's your turn. Can you help me convert 150 million kilometers to meters, please?
I
Same
believe
method
I
that Jenna used a second ago.
So that would be, I mean, I don't know if you want me to say it in scientific notation for the equals,
I
but
just want you to tell me all the steps.
Yeah. Yep. So you would put the thing you're trying to convert, which is 150 times 10 to the 6th kilometers.
Good.
You would multiply that by a division bar.
Good.
You would put the units on top and bottom. So kilometers would be on the bottom and meters on top. And then you would plug in the numbers. So it would be 1 kilometer on the bottom and 1,000 meters on top.
Let's see if you can do the same method we did before. Think about the number of zeros you have and tell me how to write the answer without using a calculator.
So just 150 times 10 to the 9th kilometers.
Kilometers?
Or meters, by that, sorry.
Beautiful. I like the way Ian did that, and I liked his speed. That's the kind of speed you're going to need to succeed during the test. No doubts. He just did everything just the way I wanted it. Okay, now we're ready to punch in the numbers. Let's set it up. The force of gravity between the sun and the earth is equal to, big old division bar, 7 times 10 to the minus 11, because big G is always the same. The units are meters cubed per kilogram per second squared, times the mass of the sun, 2 times 10 to the 30 kilograms, times the mass of the earth, 6 times 10 to the 24 kilograms, divided by the distance between them squared, 150 billion meters squared. Okay, write that down, and then I want you guys to punch it up without my help this time and just tell me the answer, rounded and everything. So I want to get to the point where I can tell you guys, punch them up, and you'll just do it and do it right. That's where I want to be. And while you do that, I will peruse the Principia Mathematica for wisdom. Of the chapter 7 of the attractive forces of spherical bodies. 154.
Do you want me to just read out the answer, or are we all just trying to do it individually?
I want you to read out the answer. I'm just looking for this famous quote. I'm just giving everyone a chance to catch up to Ian, that's all.
Oh, I'm not worried about it, yeah.
All right, okay. Tell me what you got, Ian.
I got, do you want it rounded?
Of course I do.
All right, then I would say 4 times 10 to the 22nd.
Excellent. And the units?
Newtons.
All right. Let's take a pause here and just check up on everyone else. Did you guys get the same thing that Ian did? That's the correct answer.
I
Kim, yes.
keep getting 2 times 10 to the 22nd.
Oh, can I hold it up? Hold it up. Good, Yudi. I'm glad you're there in the background. Hold it up. That's what happens if you hit d squared. Now hit equals. Just hit equals and see what you get. Just punch equals.
Oh yeah.
So what happens is, look at me, Jenna. Let me explain what you did wrong. When you square something, let's say I hit 2, oh, let's do a different one. Let's say I do 3 squared. It immediately shows you the square, but then you have to hit equals to complete the calculation. So don't make that mistake. How about Nori? Talk to me, Nori.
It worked out for me. I got 3.73.
Yep, times 10 to the 22. Okay.
And then
And it sounds like some background trolls got it too. That's good. Okay, so Ian, what have we learned? Is the force of gravity stronger between the sun and the earth? Or is the force of gravity stronger between the earth and the moon?
Definitely seems stronger between the sun and the earth.
So that was a surprise, right? Okay,
Yeah.
here's something I want you to be able to do in your head. So no calculators allowed for a second. I'm going to ask us to compare the two forces. And this is how this works. Compare the sun-earth gravity to the earth and moon gravity. Since the force of gravity between the sun and earth is bigger, we'll divide the sun and earth gravity by the earth and moon gravity. That gives us 4 times 10 to the 22 newtons divided by 2 times 10 to the 20 newtons. Ian, do you know how to do this without calculators? If
Sorry,
not,
1 second. Writing stuff down. Sorry, 1 second. I'm still writing some stuff down.
all right, sure. Write it down and then we'll talk.
All right. I think you would.
Okay. No.
Would,
If you have to think, you don't know how to do it.
well, I think I'm saying I think it would be 2 times 10 to the 1 to the 20. Sorry, to the second.
That's
so
right.
Just 2.
So, all right, good. 4 divided by 2 is 2. You subtract powers. 22 minus 20 is 2. The units cancel. What is that in plain old English? What's that number?
That is 200.
That's right. What is the meaning of the 200?
That I am not sure.
percent.
It's not percent. Well, no, not really.
Is it 200 times stronger?
That's right. The sun's gravity on Earth is 200 times stronger than the moon's gravity. That's what that means. Ian, we live in the ocean state. There's a bay a few blocks from my apartment. There are tides. I can see them twice a day, high tide and low tide. I can watch the water come up and stain the bricks, and then as it recedes, I can see where the high mark of the water was. I'm sure you guys have seen the same. What causes the tides?
The moon.
Is the tides caused by gravity?
Yes.
Why doesn't the sun cause tides if its gravity is 200 times stronger?
If I had to make a guess, I would say because it's so much further away.
But
But-
yet, didn't we account for distance in our equation of gravity? Because this is how you got yourself in trouble in the first place. You said, I think the
Yeah.
moon's gravity will be stronger because it's closer. And yet, when we plugged the distance into the equation, it still didn't matter. And the reason why it didn't matter, if you didn't notice, I erased it now, is the sun's mass is 2 followed by 30 zeros, kind of a big number. So what is it? I mean, does distance cause tides or does gravity cause tides? Yeah, the moon might be closer, but the gravity from the sun is stronger. Doesn't that seem weird to you?
yeah, very.
Okay. You've stumbled onto an important riddle. Tides are fucking complicated, okay? They're not as simple as you think. Let's do a module on that because it comes up in our homework today. I've got to do this quicker than I would like to do because I've got some other stuff to do before class ends. Today's homework, by the way, is going to be hard, okay? So hang on to your hats. I've got to do a couple of things before we're ready, but the first thing I got to do is talk about tides. So let's have a moment to talk about the tidal force, which is its own unique concept, okay? Let's put some bullet points down for us to meditate on. The first one is that, yes, Ian, tides are caused by gravity. That's a fair thing to say. But although tides are caused by gravity, the so-called tidal force is not the same thing as the gravitational force. The tidal force is not the gravitational force. There's a difference. And the difference is this. The tidal force is okay, I want you to wait for a fancy term here. It's a differential force. And I want you to underline differential force because that is a key phrase. The tidal force is a differential force caused by gravity acting over an extended body. To make it more mathematical, the tidal force, it's kind of like a delta force. It's a change in force, a difference in force. It's the difference between the force that acts on the front of a planet like Earth, subtracted from the force of gravity that acts on the back of a planet like Earth. And that difference in force is what causes tides. In fact, in the language of calculus, the tidal force is the gradient or the derivative of the force. And the tidal force famously is not proportional to 1 over the distance squared, but to bust out our proportionality operator, weirdly, the tidal force is proportional to 1 over the distance cubed. This is what makes its distance dependency a little bit weird. But this you can put in parentheses. This is for advanced students only. That's not for your everyday student. Take all those notes down and then I'll try to explain it with a cartoon. Okay. Nori, give me a thumbs up when you're done copying. Okay, let me make this cartoon as simple and as quick as I can. So here's the moon. And here's Earth. And you know from our previous problem, excuse me, the center to center distance is 384,000. We'll do the whole thing in kilometers. The radius of Earth is 6,400 kilometers. 6 times 2 is 13. Sorry, 6 times 2 is 12. 4 times 2 is 8. And that means the entire diameter of Earth is 12,800 kilometers. Tell me, what percentage of the distance between Earth and the moon does the diameter of Earth comprise? So if I were to ask, if you consider the front of Earth versus the back of the Earth, what percentage is that of the distance between the Earth and the moon? In other words, take your calculators and hit divide. And then read me the number.
0.33 repeating.
Say that again, Kim.
0.33 repeating.
You said that wrong. You did not say what you see on your calculator. You said the wrong thing. Say it again. Say it better.
Well, it's 33%.
That's totally incorrect. Kim, it's time for us to have some learning, okay? Watch me, bud. 12,800 divided by 384,000. Now, you read that to me as 0.33. Is that what you see?
No,
What do you see?
0.033 repeating.
Let's just call it 0.03 for simplicity. What is that as a percentage, Kim?
3%.
Thank you. Now, did you type it wrong or did you say it wrong?
I said it wrong.
But you'll never do that again.
No.
All right. Don't ignore that zero. That zero matters. Okay. In other words, Kim, the front side of Earth is 3% closer to the moon than the back side of Earth. That's a small percent, but it's significant. Hell, I barely get a 3% raise every 5 years, okay? And I appreciate it when I do. All right, this year they took it away from me. I don't know why. But okay, that's just me complaining. Let me make a cartoon picture out of this. Imagine that the moon is tugging at all points on the Earth, because the Earth, it's not a point particle. The Earth is a collection of bits of rock and metal. So the front side of Earth feels a tug from the moon, and the back side of Earth feels a tug from the moon. But the front side is going to get tugged a little bit stronger because distance matters, and it's 3% closer. In other words, if I could really cartoonify the problem, let's imagine that the front side of Earth gets tugged with a force of, I don't know, we'll make a little thin slice of Earth so that it's a very small amount of mass. Let's say the front side of Earth gets tugged with a force of 40 newtons. And let's say that the back side of Earth gets tugged with a force of 10 newtons. A slight difference in force. Then the tidal force that the Earth will experience is 40 newtons minus 10 newtons is a 30 Newton differential at acting across its body. And that means the Earth is actually feeling a shear force, a pulling apart or a stretching force from its front to its back. And there's two ways to look at that. In the top picture, you can see that the front force is tugging harder than the back force. And that causes the oceans to bulge both in the direction of the moon and opposite the moon as well. Now, if you think about it from an Earth-based reference frame, Earth can feel the 30 Newton differential across its body, so it kind of feels like it's being ripped side to side apart. And that's what makes the bulge also occur away from the moon. Another possible way to think about it is the front side gets the strongest tug, the middle gets the second strongest tug, and the back side gets the weakest tug, and it pulls the center away from the back. Not only does the Earth's water bulge in the direction of the moon, but Earth's atmosphere also bulges in the direction of the moon. There's atmospheric tides. And here's what's really crazy. The ground rock underneath your feet itself deform in the direction of the moon. And each day, the rock under your feet is pulled towards the moon by about 3 centimeters. It actually pulls the crust of Earth in the direction of the moon. There are rock tides as well as water tides. Other planets in our solar system, which have larger masses nearby, can experience even more intense versions of this. And we'll show you some of those later on. For now, however, let's pretend you're a pesky student. A pesky student could ask me, well, geez, Brendan, okay, so there's a differential force. The front side's tugged harder than the back side. That makes sense. But didn't we calculate that the moon's force was 400, didn't we calculate that the sun is tugging on Earth 200 times greater? Shouldn't there still be the same thing going on with the sun? And I would say, okay, yes, but consider this. The distance to the sun is 150 million kilometers. And in the interest of time, I'll plug it in. If you do 12,800 kilometers by 150 million, that's 9 times 10 to the negative 5, or 9 thousandths of 1%. The percentage difference between the front of Earth and the back of Earth relative to the sun is way, way smaller, a fraction of the Earth-Sun distance. So let's say the sun did tug on the front side of Earth stronger. Let's say instead of 40 newtons, let's say the sun tugs on the front side by 400 newtons. By the time you get to the back side of Earth, the tug will only have shrunk by a small amount. And let's say that the sun will only tug on the back side of Earth 399 newtons. So for the sun, the delta force will be the difference between 400 newtons minus 399 newtons equals only a 1 Newton differential. Therefore, it is possible to say two things which sound incompatible but actually are. The sun, the gravity from the sun tugs on Earth stronger than the moon at all points, but the differential force from the moon, the tidal force, is stronger than the differential force that the sun tugs on the Earth. Do you see? I said that wrong. The differential force on Earth from the moon is stronger than the differential force on the Earth from the sun. Hopefully these numbers explain what my words failed.
I was kind of right.
In a way you were, because the distance is part of the issue, isn't it, Ian?
It's just not the whole picture.
It's right. The whole picture is subtle. And I was conscious of that, but I thought we needed to go through this. You were right in a way, but it's not really the distance. It's the ratio of the diameter of Earth to the distance, right? That would have been a better. If you had said that, then you really got me. Nori.
So I was wondering, like, first when you did like the 40 newtons and the 10 newtons for the moon, I was wondering why you subtracted them because they're both going the same direction.
Ah, that's a great question. If you're getting tugged stronger on the front side and weaker on the back side, if you wrap your mind around this for a second, that's the equivalent of being pulled side to side. Because you're getting yanked harder from the front than you are from the back, so you will experience a gradient of force across your body.
Oh,
Does
okay.
that sort of make sense?
I get it.
And that picture did try to
Yeah.
show it, that if you're getting tugged harder from the front and weaker from the back, from the perspective of the Earth is floating in space and just feels a harder tug on one side than the other, so they feel like they're being stretched apart. It's a question of kind of reference frame or something. It's equivalent to the same thing. I'm trying to think of a way you
It's
could
like-
prove that to yourself, but it's not coming to my mind. I guess you'd have to get some friends.
No, like,
Yeah.
say like if like both, if you were like pulling them both 40, it would go. But like if you, because it's only being pulled 10, like technically it's being pulled 30 back. So that's
Yeah.
like what we got.
They call that side-to-side force a shear force. You feel a pulling apart or a stretching force, right? If you're tugged harder on your left arm than on your right arm, you will also feel a pull against your two arms. Now, let's talk about another subtle fact that every good Rhode Island caw hogger probably knows about. Even though the sun's differential force is way less than the moon's, the sun actually still contributes to tides. And as every good fisherman knows, every month we get unusually potent tides during the new moon and the full moon. New moon and full moon has an alignment between sun and earth, and the sun gives the moon an extra boost. We get unusually potent tides called spring tides. And each month at first quarter moon and at third quarter moon, we get something called neap tides. They're wimpier than average tides. That's where the sun's differential kind of weakens the effect of the moon's tides. So tides, if you follow them over the course of a month, there are higher than average high tides, and then there are lower than average high tides. Just in case I want you to recall this at some point, you can take notes on that. Spring tides are strong tides at full or new moon. Neap tides are weaker tides at first and third quarter moon. Okay. Class, I did that as quick as I could. Tides are obviously complicated. They take some time to explain, but I feel like you guys understand me. I need to introduce one more formula, or our homework today is really, really, really going to suck, okay? Our homework's going to suck today no matter what. But there's going to be a new formula, which is kind of crazy, and I just want to take 5 minutes to introduce it, to put it into your notes, and then we'll do it together during the homework. I'm going to erase. Okay. Up to now, this week, I've done two things with you to explain the works of Sir Isaac Newton. I told you that Newton had given us two important concepts in Principia Mathematica. The first were his laws of motion. And of his three laws of motion, the most important is the second law, which defines a force. F equals ma not only defines a force, but it tells you if you tug with this force on this mass, the mass will experience this acceleration. So in a way, this formula, although it's not obvious, tells you how things move or accelerate when you push them. He also did another thing. He gave us the law of gravitation. The law of gravitation was a way of calculating the actual force of gravity between two masses. The thing that he did next is really complicated because it's very mathematical, but I can sort of explain the concept. He combined his laws of motion with his laws of gravitation to actually analyze the orbits of different bodies around the solar system. For instance, you know he cared about the moon, so he applied these two formulas to the orbit of the moon in a way that Nori was kind of asking me, how does the tug and the velocity cause the moon to go around in a circle? That's what he did. He analyzed that motion using these two equations. And it's in the Principia. Now, if you combine these, you can rederive all of the different laws of planetary orbits that Kepler had worked out, but you can make new, more powerful versions. And he combined them to make what we call in our class Newton's version of Kepler's laws. Basically, he improved Kepler's laws so that they would work in a variety of different situations. I don't have time to go into all three of the things he did. I'll probably cover that a bit next class. But one of the equations we're going to need for our homework today. So let's focus on just the third law. For instance, let's look at the difference between Kepler's third law and what we're going to call Newton's version of Kepler's third law. Actually, saying Newton's version of Kepler's third law is kind of irritating. So I'm going to refer to that in the future as NK3. Why don't you guys help me by reminding me what Kepler's third law of planetary motion was? If you need to consult your notes, then do it.
Is harmonic law. So
Okay.
P equals A cubed.
Okay, so we have P squared is equal to A cubed. And what do the things mean?
P is the period of planets in years, and A is the average distance between planet and the sun in AU.
So I'm going to do shorthand versions. P is period in years. A is distance in AU. Here's the thing about Kepler's third law. It only works for orbits that go around the sun. So for instance, it will work for planets or comets, but it will not work to describe the orbit of the moon around Earth or the moons of Jupiter. Isaac Newton came up with a way crazier version that would work for any two orbiting masses, but he had to include the effects of gravity. So here's what Newton's version looks like. P squared is equal to 4 times pi squared times A cubed. So we still have P squared and A cubed divided by big G, the gravitational constant, times open parentheses, the sum of mass 1 plus mass 2. The units are not the same as the Kepler version. Newtons have to be MKS. So the period must be measured in seconds. The A must be measured in meters. And take a guess, kids, what are the masses going to be measured in? Oh God, someone please. What do we measure masses in?
Kilograms?
Kilograms, that's right. The importance of the Newtonian version of this equation, it's definitely an improvement because unlike Kepler, which only works for planets going around the sun, this works for any orbiting masses. Just like plugging into the law of gravity caused us, actually, you guys did pretty well. Most of you got it right the first time, and the two mistakes we fixed quite quickly. So that actually gives me hope that maybe today's homework will go smoother than I was thinking. But just trust me that plugging into this equation the first time around, it's kind of a challenge. However, we are out of time for our lecture today. In fact, I'm over a little bit. Well, I don't know what computer time is. There's computer time, 1:30 computer time, so in a sense. This formula is going to be in our homework today, so we'll practice it when we do the homework. Sound like a plan? All right. Let's take 15 minutes or so to chill and drink some tea. And when we come back, we will tackle the homework for chapter 4. Sound like a plan, guys? All right, it's 1:35 for iPhone time. So 1:50 iPhone time, I will return. Okay? I'll see you guys then. Well, everyone, only one snack made sense today during tea break.
Yeah.
Wow, legendary.
Let's do some real Newtons over here. Let's get down to our homework. Could everyone please call up the questions so I can get some question aid reading those things? See if we can reuse one of these pups.
We're on 4 right now, right? Or 5?
Chapter 4, homework 4, yeah.
Yeah, okay, perfect. 4 is chapter 4, questions 45, 47. Yeah, you're still erasing.
Oh, I'm sorry. This
No, you're fine.
preserves the markers a bit longer. I should have waited to pause the video, but I guess the students later can watch it. All right, so we have name. We have AS1010 plus your section. And then we have homework number 4. Questions are chapter 4. Ian, hit me again.
Questions 45, 47, 56, 57, A, B, and C only, and 58, A and C only.
I'm going to reduce our workload today just based on what happened in the last homework session that I did on this. It just took a little bit too much time. And what was the last one?
58 A and C.
I'm going to reduce it to just A and B and 58A. I think that'll keep us busy enough for today. That way we can kind of manage this in a timely fashion. Oh no! Got some goo on my calculator here. Okay. All right. Ian, since you're all queued up,
Yep.
why don't you hit me with chapter 4, number 45?
All right, 45, the gravitational law. And it says for A, how does quadrupling the distance between two objects affect the gravitational force between them?
And what's quadrupling mean again?
Multiplying it by 4.
So the distance is 4 times greater. Okay, Ian, why don't you help us? How do we set up our proportionality argument here? The force of gravity is proportional to.
Yeah,
Oh, right.
let me pull up my notes. Right, force of gravity. So, yeah.
God damn, these things are good.
Okay, so we would be doing the first thing we looked at. So that would be force of gravity is proportional to m1 times m2 over d squared.
Well, we're not changing all of those quantities here, so we can make it simpler.
Yeah, well, I was about to say, but for that you would plug in the 2 for d, so it would be,
No.
right? No?
I want you to
Wrong.
write it symbolically first, leaving only those variables that we are modifying.
Oh, okay, sure. Then would it be 1 over d squared?
That's right. Or to use Newton's terminology, the force is inversely proportional to the square of the distance. Inversely proportional means d is on the bottom. Square means there's a little 2 there. Now, we can sum stuff in. Tell me what to write.
Initially you could just write 1 over 2 squared.
Why 2?
Or no, sorry, 4, because we're quadrupling it. Sorry, I was thinking about the one we did in the notes.
Now this becomes an equality because I can actually calculate that.
Yeah. So it would end up being 1/16.
Sorry?
1/16.
Yep. And what's the meaning of 1/16?
It is 16 times weaker. The force is 16 times weaker. Force of gravity.
The new force is 16 times weaker, or 1/16. Excellent. This day might not be as bad as I thought, if you guys can already do that. Okay.
B, are we doing B and C?
Yeah.
Okay. B says, suppose the sun were somehow replaced by a star with twice as much mass. What would happen to the gravitational force between Earth and the sun?
Let's have someone else try it. Maybe Kim. Kim, how would I set this up?
It would be force is approximately
Not approximately, proportional to.
proportionally, sorry. 2 times 1, so
No.
2.
First, I want you to write it symbolically, then we'll substitute
Okay.
it. See here, we wrote it
So-
symbolically.
So it would be m1 times m2.
Are we adjusting both masses here?
No, just
We're
one.
only-
So the sun, so it's just just put M1.
Sure, either one, but M1's fine. And now we'll make another proportional 2 symbol. And by what factor are we adjusting the mass?
2.
So we'll substitute in 2. And kind of we're done at that point. What's the meaning?
The mass is 2
No, we're interested in the
kilograms.
force.
The force is 2 kilograms.
No. Okay, hold on. This
Right?
number does not have units. It does
Okay.
not mean 2 kilograms, nor does it mean 2 newtons, but I think I could have a second one. Okay. I hope it means 2 newtons. Okay. No, it doesn't mean 2 newtons either, unfortunately. The force means 2 what?
It's 2 times greater.
That's right. That's what it means. The new force is 2 times greater than the old force. Mm. Ian, how about part C?
Okay. C says, suppose the Earth were moved to 1/3 of its current distance from the sun. What would happen to the gravitational force between Earth and the sun?
Okay. Jenna, my friend, why don't you help me set this one out?
Okay. So we'll do F is proportionate to D 1 over D squared.
D with an over D squared?
I'm sorry, no, just 1 over D squared.
Oh, okay. That sounds much better. All right. I don't like the way I wrote that. I'm going to fix that. Okay, which is proportional to, now what do I write?
One over 3 squared.
No. That is not how we do it. That's not okay. You did something wrong. What was it?
I did tripled instead of 1/3.
All right. So instead I should write
Oh, 1/3 squared.
but we have to be careful how we write this, Jenna. We should write it as 1/3 in parentheses squared, because the square must be distributed to both parts of that fraction. Now we can turn it into an equal sign. Jenna, help me distribute the square.
So it would be 1 over 1/9.
That's right. And what does that reduce to? What is 1 divided by 1/9?
Is it 9?
That's right. The bottom of the bottom is the top. So what have we learned?
That the new force is 9 times greater.
Very good. Or 9 times stronger. And this is a simple taste of how we use our proportionality arguments. It's also the answer to our first problem.
I have a question.
Yeah, sure.
So just like a quick recap of like knowing whether it's stronger or weaker. If it comes out as like a whole number, then it's stronger. But if it comes out a fraction, then it's the bottom number weaker.
Yep. if it comes out
Or am
as
I
a whole number,
understanding it wrong?
no, that's right. It's the new force is how many times the old force. If the new force is 3 times the old force, then it's stronger. If the new force is 1/3 the old force, it's weaker. But it doesn't have to be a whole number. It could be some irrational number. Like suppose we moved it to, instead of 1/3, ask yourself what it would be if we had made it 2/3. If we had made it 2/3, the new force would be 9/4. It would be stronger, but that would not be a whole number because 9/4 is 2.25. So I agree that if the number is bigger than 1, the force is stronger, and if it's less than 1, it's weaker. But I do not agree that it needs to be a whole number because according to the rules of math, 2.25 is not a whole number. Does that make sense?
Yeah.
Okay.
Thank you.
This is a good start. We'll learn how to use this as we go forward. I'm erasing. Okay, Nori, could you call up chapter 447 and read that puppy off for me?
Head to foot tides. That's the little title.
Yep.
You and Earth attract each other gravitationally, so you should also be subject to a tidal force resulting from the difference between the gravitational attraction felt by your feet and felt by your head, at least when you're standing. Explain why you can't feel this tidal force.
All right. Let's draw a picture so that we can understand exactly what this question is asking. Over here on the left, make a circle to represent Earth. And I want to draw an Earth's radius vertically. The radius of Earth, per our discussion today, is 6,400 kilometers. Now let's draw a person standing on Earth. What would you guys say the typical height of a person is?
5'8".
Okay, in Lemass imperial units maybe, but that's not helpful. How about in meters?
Isn't it like, I don't know exactly, but isn't it like 1.5 or something meters?
I mean, I'm at 1.8 or more.
Okay.
So let's say 2 meters, just to round up simply. Sometimes people say the typical height of a man is close to 2 meters. And what this question is implying is that your feet and your head are both experiencing a gravitational force towards the center of Earth. But your feet are 2 meters closer to the center of Earth. So there should be a force, just like we talked about in today's class. Let's call it F sub foot, a force acting on your foot, which is ever so slightly different from this other force, the force acting on your head, F sub head. And that's because your head is a little bit farther away from the center of Earth than your feet. Thus, you should be subject to a tidal force stretching you apart. The question is, why don't we feel this force? What's the answer? Based on our discussion in today's class.
Do both of the forces, like the difference between like the force of your head and like the force of your feet, do they like cancel each other out, or are they too little to like notice?
They don't cancel each other out. Actually, neither of what you said is technically true, okay? They don't cancel each
Okay.
other. But let's analyze. So learning how to talk science, the point of a word problem is how do I talk science without making a mistake, okay? Let's first address your question of canceling out. Both forces pull in the same direction, so they don't cancel out. If anything, they add together. The second thing you said is they're too small to notice. If the forces were too small to notice, Nori, then I would be able to jump up into outer space and Earth would not pull me back down. But unfortunately, I seem to be stuck to this stupid thing. And so I can definitely feel that force. If I fall off a ladder, then the force is all too real and not negligible. But that's if you're talking about the force. The tidal force is not the force.
Would it be because it diffuses?
Diffuses?
Like
Like
when we were
molecules going up into the air? Or?
well, like when we were talking about the moon, how it kind of I think you said it was like a gradient that goes around it.
Okay. Now, gradient is a better word.
Okay, yeah.
Tell me about gradients. Diffusion means like molecules dispersing into the atmosphere. So that word doesn't seem to apply here. But if
Yeah,
you want to talk gradients, then I'm all ears.
Yeah, this is something I'm still trying to like wrap my head around about like how exactly it functions, but where.
All right, let me teach you how to say the answer right. Use all the buzzwords that I taught you in your bullet points today. Try to answer this in terms of those buzz phrases.
Don't they differentiate?
Not differentiate.
Differential force.
Differential force. Okay, so tell me about the differential force. Now you've got my attention. What's up with the differential force? I got two forces. Tell me about differentials. Today, when I talked about the moon and the sun, I asked us to consider what percentage the diameter of Earth was compared to the Earth-Moon distance. How many meters is the radius of Earth? You can't really compare meters and kilometers that easily. How many meters is the radius of Earth?
It would be 64 times 10 to the 5th.
Which is the same thing as 6.4 times 10 to the 6. In other words, it's 2 meters versus 6 million meters. The radius of Earth is 3 million times bigger than the height of a man. Does that help? No one could do this?
I mean, I'm still trying to like get it right in my head, like how this works. So I'm sure if I understood it better, that would have helped.
The tidal force is a differential force. It's the difference between the force on your foot, should be a little bit stronger, right? Minus the force on your head. They're trying to say, why can't I feel a tidal force, a difference of force between my foot and my head?
Is it because we're such a small percentage of the Earth's radius?
That, keep going, that's the first part. We are such a small percentage of Earth's radius that
We won't feel the difference in force
because
on
these
ourselves.
forces are essentially the same. This force, if it tugs with 10 newtons, is also going to be 10 newtons up here are almost the same because it's such a small difference compared to the radius of Earth. Yeah, it's the difference in the force is basically 0 because these two numbers are the same. That's not the same as saying these forces are 0, which is how Nori put it. Nori was trying to tell me that these forces themselves are 0. That's clearly not true, or I wouldn't stick to Earth. But if these forces are non-zero, but wicked freaking close to each other, then 10 minus 9.999999999 is essentially 0, right? Let's write it this way. A person will not feel a tidal force acting across, let's say acting along the height of their body. A person will not feel a tidal force acting along the height of their body. My markers are all getting kind of pooped out here, so I think it's time for a freshie. Have I got a freshie nearby? Yeah, I'll burn this one out and then I'll start with a freshie. A person will not feel a tidal force acting along the height of their body because the 2-meter height of a person is millions of times smaller than the radius of Earth. So now we talked about the distance percentage. Now we're going to talk about the tidal force itself. Ow. Ow. Therefore, the difference in force between Earth's gravity on your feet and Earth's gravity on your head is essentially, and if you want in parentheses, you could write, but not quite, 0. There are places in the solar system where this gradient in force is very much not 0. And one of the most famous and legendary situations is that of Mars's moon, Phobos, I believe. The moon Phobos, although small, is close enough to Mars that the gradient of force across the front of the moon and the back of the moon is actually getting strong enough to exceed the self-gravitation of this overgrown asteroid. The tidal force is comparable to the self-cohesion of the rock. Astronomers predict that in the next million years, Mars's moon Phobos will be ripped apart by its own tidal forces and torn into a rubble of dusty disk that will orbit the planet like a dust ring for years afterwards. So sometimes astronomical objects can be pulled apart by these tidal forces. I wanted to mention this in class today. Speaking of Mars, I hate to throw this in during office hours, but maybe more people will listen. There's kind of a cool thing happening tomorrow. The Mars Perseverance lander is scheduled to attempt to land on Mars. Washington Post, Mars Perseverance. Do I have that right? This was in yesterday's Washington Post, and I can put the link in the chat, but if you type Wash Post Mars Perseverance, tomorrow Mars's new lander, the Perseverance, is going to attempt to land on Mars. And this thing is a big tank that does all kinds of cool science. It's really wild. Just check out this video here. It's going to be flying towards Mars at an extremely rapid velocity. It's going to try to slow down and brake on Mars's thin atmosphere. Then the heat shield is going to pop off, and this little
Riding a bike should be a really fun experience.
We'll do
We
that
make
today.
low-maintenance bicycles
Bastards.
for everyday riders. We were coming off a great year, and when the
can I
pandemic
use
hit, we really had to
I wanted
think
to show you the video
creatively.
because it's
Teams allowed us to do what we call virtual visits. Hey, is that TK?
there we go. Okay.
Traffic. We all hate traffic.
No.
What?
What?
And if you're standing in Washington,
Okay.
D.C.,
That's lame. I thought this was going to be a video. Maybe I skipped it. Anyways, this is the little trajectory. Tomorrow, the orbiting craft is going to hit the atmosphere. It's going to slow down and brake. Then the heat shield pops off, and that little flying rocket is going to take it to the landing site and deposit the rover by crane. It's like a totally wild thing. Yeah, there's a parachute to slow it down, and then the heat shield pops off, and then this little rocket is going to shoot some jets out, and it's going to kind of pick the perfect landing site and deposit the tank with a little crane. It's a very, very delicate landing. They call it 9 minutes of terror, where all of these scientists who spent like the last 10 years of their life working on this have just 9 minutes of prayer that nothing goes wrong. Once it lands on the surface, they'll be in good standing. But that's kind of like a cool solar system exploration thing and something you should be aware of. So give that a peek tomorrow if you're sitting around. Open up some news app and see how the landing goes. It'll probably be broadcast live on NASA's website. Okay, 47's down the hatch. On to 56. Let's see. Ian read, Nori read. Jenna, you want to read us 56?
Yep, sure. It's understanding Newton's version of Kepler's third law. Find the orbital.
NK3.
Yep. Find the orbital period for the planet in each case. Hint: the calculations for this problem are so simple that you won't need a calculator.
False.
And-
That's a lie.
Okay.
All right. First, before she reads it, let's write down NK3. P squared is equal to 4 times pi squared times a cubed divided by g times the sum of the masses. Go ahead and write that down, Jenna, before you start to read. This is the new improved version of Kepler's third law. I'm so mad about that video. That video is supposed to be the video of the Mars lander, and they cheated me.
It always, YouTube always plays commercials first before it goes to the video.
Right, but what irritates me is when I skipped it, they clearly jumped over that video. Like they always show you the next one. So it's too bad because I watched it during tea break and you could see like a video of the heat shield coming off and the rock. It was just cool. So I'm just mad. What's A, Jenna?
A planet with twice Earth's mass orbiting at a distance of 1 AU from a star with the same mass as the sun.
Okay, it's time for you guys to learn some symbols that we're going to be using going forward in this class. The circle with a cross is the astrological symbol for Earth. So when I want to represent the mass of Earth, I write mass with a little subscript of circle cross. Likewise, the symbol for the sun is a circle with a dot in it. So astronomers often use a circle with a dot to represent the sun. So in other words, it's a planet with twice Earth's mass orbiting the sun at a distance of 1 AU. Our goal is to calculate the period. How should we begin? Let's first identify all the variables. We know 4, we know pi, we know square, we know g. What's the A? What is A in this problem? Can't identify A, can't do the problem.
A is the distance in meters.
Okay, so the distance they gave us was 1 AU. And you know that 1 AU is 150 million kilometers. Ian, what do we do to get that into meters?
We would do the, forget your name for it, but the conversion equation.
Okay,
No.
so division bar?
Yep. And then you would put kilometers on the bottom and meters on top.
Yep.
And 1,000 meters over 1 kilometer.
And now let's do that in our head to speed things up. You can do that in your head, right?
Oh yeah, sorry, I'm just writing stuff down. So that would be 150 million, 150 billion
Nice.
meters.
I like your moves. Okay, that takes care of our A. That's convenient. We'll let Ian catch up on the writing here. Now I want to focus on M1 plus M2. What are those masses? What are the M1 and the M2?
Those
Earth
are,
and the sun.
Not quite. One of them is the sun.
the other one is 2 times the mass of the Earth.
All right. Sometimes it's customary to refer to this M1 plus M2 as the total mass of the system. And let's analyze the total mass together for a second. The total mass of the system is 1 times the mass of the sun plus 2 times the mass of Earth. And now I'm going to substitute values in. The mass of the sun is 2 times 10 to the 30 kilograms plus 2 times the mass of the Earth, 6 times 10 to the 24 kilograms. I want you guys to punch that into your calculators. Tell me what you get. Valentina, I want to hear what you get.
I got 2 times 10 to the 30.
What are your units?
Kilograms.
Okay, that's cool, Valentina, but you know why that sounds weird to me? You just added 2 times 10 to the 30 kilograms, the mass of the sun, plus twice the mass of the Earth, but all you're saying you got was 2 times 10 to the 30 kilograms? Doesn't that seem kind of weird?
Yeah.
So what do you think happened there?
I did something wrong.
No, you did something right. But that doesn't mean you understand it. We need to understand it. How can you add the mass of the sun plus twice the mass of Earth and just get the mass of the sun? Can someone answer that riddle to me?
The mass of Earth is just so small compared to the mass of the sun. So
That's
you
right.
can-
Valentina, this is a 2 followed by 30 zeros. This is a 6 followed by 24 zeros. There are 6 more zeros in this number than there are in this number. Valentina, do you know what $1 million plus $1 is equal to?
Yeah, 1,000,001.
No, $1 million, because the $1 doesn't fucking matter. Okay, so you can't buy anything with $1. Well, not much. The thing is, you're at, in fact, it wasn't quite, the mass of twice Earth is so small that it only appears way out here at the 7th or 8th decimal place, right? So this is a trick that you have to know when you can play it. Sometimes one of the masses is so small in comparison to the other that you can kind of cancel it out and you can neglect one of the masses. And you can basically say that the total mass is approximately equal to the mass of the sun with no change in the accuracy of the calculation. But you guys have to know when to play that trick. Sometimes you can play it, sometimes you can't. So what we're going to do next is we have our A, and we've replaced the sum of the masses with the mass of the sun, because it's about the same. And now we're going to take the square root and we're going to calculate all that. So let me know when you're done, because I have to erase this to make more room. Ian's done. Jen is done. Nori, give me that thumbs up when you're done. Valentina, Kim? Okay. You're good, Kim? All right. All right, so we're still on part A. I'm going to do 2 steps at once. I'm going to take the square and put it on the other side. So it's going to be like that. And now I'm going to put all the values in, okay? So P is equal to the nice big neat square root of 4 times pi squared times open parentheses 150 billion meters cubed divided by big G 7 times 10 to the minus 11 meters cubed per kilogram per second squared times just the mass of the sun, 2 times 10 to the 30 kilograms. All right. Punching this in is going to be an adventure. let's talk strategies. Here's how this is going to work. When we punch, we're going to punch together in just a minute, but I want you to listen to my logic, okay? I'm going to do 4 times pi squared times, I'm not going to use any parentheses, times 150 exp9. Then I'm going to cube it. Now listen carefully. Then I'm going to divide by big G, 7 exp minus 11. But when I get to this step, I'm not going to hit times. I'm going to hit divide again so that the calculator knows the 2 exp30 is also on the bottom. Then I'm going to hit equals, and then we're going to square root at the end. Okay? All y'all ready to try that together? Do this in memory of me. Let me adjust my focus. Help you see the calculator better. Okay. You ready to go? I'm going to try to go slow for you guys. 4 times pi squared times 150 exp9 shift x cubed divided by 7 exp negative 11 divided by 2 exp 30. Now we hit equals, and now we have to square root. Shift square root. Show me that. Everyone, very good. Very, very good. Everyone except for Kim. Kim, show me. You're muted, bud.
I missed a key, so I had to retype it in.
Okay. Show me when you got it. Everyone else, Jenna, Ian, Valentina, Nori, you did a great job. The question is, will you remember all that? We'll find out in a second. Kim, why don't you show me what you got? Because there's no point moving on unless everyone's together.
So when we do 7 times 10 to negative 11, would you divide it by the next number?
That's the key step that people screw up. You have to divide. Oh, Ian's got a cat too.
Nope.
This is cat crew. Tuesday, Thursday is dog crew. You guys are cat crew. Except I can't, Kim has an animal too, but it was a dog, right? All right.
I also have a cat. He's
Cool.
sleeping.
Kim? Talk to me, you're muted.
I keep hitting the wrong key. That's what my problem is.
All right, can we do it together then? Because
Yeah.
I don't want to move forward unless you got this.
Yeah.
All right. 4 times
Yeah.
pi
Yeah.
squared
Yeah.
times
Yeah.
150
Yeah. Sorry.
exp9
Yeah.
shift cube.
Yep.
Divide by 7 exp negative
Negative.
11 divide by 2 exp 30 Kim, I'm losing you.
No, I'm here. I'm sorry. I'm just finishing it.
Equals shift square root. Did you get this?
Equals shift square root. Nope, I hit something wrong somewhere.
All right, so this is what's hard doing this over the computer here.
Yeah.
Now, I pushed every button. The right way to do this is to say, yeah, when you're done. You were doing good at first, but then
Yep.
your yeahs kind of trailed off and you're fucking around there. I don't know what you're up to. I can't see it. So did I go too fast for you or what happened?
No, I just hit the wrong key.
All right. Why don't you keep working on that? We're going to try it again in a moment. The rest of you, how do I round this? Tell me what I should put down on the page here. Here's a hint. 2 sig figs would be nice.
Would it be 3.1 times 10 to the 7th?
Nice. But what are your units?
That was my question. Would it be seconds or years?
How did you know it was going to be seconds?
Because NK3 uses the K.
You are smart. That's just the kind of thing I want people to say to me. Because this is a period, and period is time, and NK3 uses MKS, which is measured in seconds, right? Here's another way to look at it, Jenna. Watch our unit balancing. Meters cubed cancels with meters cubed. Kilograms cancels with kilograms. And 1 over seconds squared is seconds squared. But the square root of seconds squared is just seconds. Very tricky, right? Okay, we're not done. This is the answer, but I want us to convert to years. I could make you do out the long dimensional analysis, but you guys are pretty good at that. I gave you a shortcut in last class. When I introduced MKS units, I gave you a conversion factor from seconds to years. Go ahead and look that up and tell me how to do it. So Ian wasn't here last class, and Kim is wrestling with her calculator. So I need Valentina or Nori or Jenna to hook me up here.
I wasn't here last class. Wait, the lab?
You weren't here for the lab either, were you?
I can try, but I just don't pick me first.
Huh? Don't pick you first. Oh, I see.
I said I
And Nori,
can try, but don't pick me first, please.
Nori, that's right. I only see you
'Cause
on Wednesdays, right?
Yeah.
Are you keeping up with the Monday stuff?
Yeah. I just watched the lecture this morning.
Okay, cool. And you got the lab done, right?
Yeah, the lab is done. I need to submit both today.
Awesome. All right, so Valentina then, my friend. Valentina, can you tell me the number of seconds in a year?
So it will be 3.15 times 10 to the 7.
Okay, you're awesome. So why don't you do dimensional analysis with me? Let's convert this to years. Put a division bar. What units go on bottom, Valentina?
Seconds,
What units go on top, Valentina?
years.
Now tell me where the numbers go.
So on the top it will be a 1,
Yep.
and the bottom will be 3.15 times 10 to the 7.
Damn, you're good. You're so good, I don't even want to call on you anymore. You're not fun at all. All right, so could you punch that into your calculator and tell me what you get?
It will be 0.98,
Which is wicked close to,
1.
it's basically 1 year. And this is where we're supposed to stop and say, duh, of course it's going to be 1 year. If you have a planet orbiting the mass of the sun at a distance of 1 AU, well, of course its period's going to be 1 year. That's the same as Earth's, right? P squared equals A cubed. 1 AU cubed is 1 year squared. Except we needed to see how this Newton version works. So we didn't really waste our time. That was a good exercise. But notice that it came out to be what we should theoretically expect. Part B will not be so easy on us. Does everyone have this? Because I need to erase for space. All right, I'm erasing. So far, you guys have been a little more efficient than I thought you were going to be. You certainly did better than my 1020 class, so congratulate yourselves. Okay, 56B. I can't even remember who the reader was. Was that
It was
Jenna?
me. Yeah, I can read it.
All right.
A planet with Earth's mass orbiting at a distance of 1 AU from a star with 4 times the sun's mass.
Let's speed things up a bit. Ian already helped us convert 1 AU to meters. Sorry, it's 150 billion meters. Let's focus instead on the total mass of the system. The total mass will be 4 times the mass of the sun plus 1 times the mass of Earth. How do you guys feel about that?
It'll just be the mass of the, oh wait, never mind. Sorry.
Jenna, I was into what you were saying, and then you stopped yourself.
Well, it would just be the mass of the sun times 4, right?
In other words, you're saying 4 times the mass of the sun is totally going to dwarf one lousy planet mass, right? Good. If you can see that, then we can skip a step. We can neglect this because the mass of Earth is much smaller than 4 times the mass of the sun. And we can just say that the total mass is 4 times the sun's mass. That will speed things up greatly for us. Now we can go right to calculating the period. I'm very impressed. The period is going to be the square root of, make a nice big neat square root that covers everything, 4 times pi squared times open parentheses 150 billion meters cubed divided by big G, 7 times 10 to the minus 11. The units of big G are meters cubed per kilogram per second squared times 4 times the mass of the sun, 2 times 10 to the 30 kilograms. Okay, class, last time you all followed me, except Kim, during the punching of this equation. Now it's time to see if you can do it without my help. But can I give you guys a tip? This time, Valentina, Nori, Jenna, Kim, Ian, you're going to divide by G, then you will divide by 4, and then you will divide by the mass of Earth, okay? In other words, don't hit times there and there, hit divide there and there. Then hit equals, then square root. Go ahead, see if you can do it. I know you're going to fiddle with your calculators. I'm going to get some iced tea. When I come back, I want someone to have an answer for me.
Am I supposed to put the 150 times 10 to the power of 9 in brackets?
I also was thinking the same thing. I didn't, but who knows?
Because I don't remember doing it the last time.
Yeah, me either.
I don't think he did the last time. I think he just put it and then cubed it.
Okay.
He's just there.
Thank you.
to study, cube all of that.
No problem.
Oh, okay.
It's kind of good to shut the hell up sometimes so you guys can interface. I've got my iced tea. Who's got an answer?
And if we were doing it down to 2 sig figs, right?
Sure.
So I got about 2.4 times 10 to the 14th.
You got to square root it. Square root it.
You're totally right. Okay.
Just take that number and hit square root.
Yep. So that would be, let's say, 1.5 times 10 to the 7th.
Units?
And that is in seconds.
Dude, I am impressed. You guys don't suck. This is pretty amazing. Okay.
High praise.
I'm just not used to a class actually being able to get that on the second try. Okay, I'm sure some people suck. Let's get real. I'm sure some people watching at home are going to wonder how Ian got that. Just out of curiosity, Valentina, Nori, Jenna, Kim, did any of you get that too? Jenna? Whoa, whoa. Kim, you still struggling? Oh, Ryan got it. I always forget that Ryan is here. Ryan, you are the best of the trolls. You really are. And Amanda's here too. She got it. All right. Kim, are you struggling? Amanda, you're the second best of the trolls.
I can't tell if what I got is right.
Nori, it's good.
Yeah.
Okay, Yudi didn't get it. That's all right. And Kim, you didn't get it?
When I get to the cubed on the top, like when you go from 4 times pi squared to the 150 to the 9th, cubed, that's where is it hit shift?
Yeah. Okay, why don't we try
Three.
this? Can we try a little, and this will be helpful for other people too. I'm going to run you through the whole thing again for the purpose of people who didn't get it or for the benefit. Could we just try a little practice though? Cube. Let's try some cube practice, Kim. You ready?
Yeah.
I remember from math that 3 cubed is 9. So watch this. 3.
Yep.
Shift x to the power of 3. Oh, sorry. Wow, I'm stupid. 3 squared is 9.
Weird.
3 cubed is 27. Apparently, I don't remember my math. Okay. Stupid. Okay, all right. So did you get that, Kim?
Yes.
All right. So you did 3 shift cube and you got 27. That's a good sign. All right. So let's try,
that's what I have. Yep.
all right, let's try the whole thing. Wow. All right. 4 times pi squared.
Yep.
Times.
Yep.
150.
Yep.
exp9.
Yep.
Shift cube.
Yep.
Divide by.
Yep.
7 exp.
Negative 11.
Negative 11.
Yeah.
Divide by 4.
Yep.
Divide by 2 exp 30.
Yep.
Equals.
Yep.
Shift square root.
I got it that time. That's what it is. I would hit cube instead of hitting shift cubed.
Oh yeah, because cube is in orange, right? That means you have to access shift to get the orange stuff. Okay.
Yep.
By the way, if you don't hit shift, this is backspace. You can use that if you make a mistake sometimes. All right.
Okay.
Jumping Jesus. Ian, help me convert that to years using dimensional analysis and the conversion factor that Valentina provided for us in the previous exercise.
Actually, I was wondering about that so did it just, because again, I haven't done Monday's lecture yet, but so the conversion factor, is it just a coincidence that it was also 3.15 times 10 to the 7th, or is it literally what we got plugged into the bottom?
This is my face. Okay. It is a truth, Ian. I wouldn't call it a coincidence. I would say that 1 year, astronomers remember it as pi times 10 to the 7 seconds. I know pi is actually 3.14, but who gives a crap?
Okay.
So this is just the truth. If you work it out, that's what it happens to be.
Okay.
Now, there is a reason why these numbers are coming out with the same power, but let's get to that later. For now, could you just convert this to years for me?
Sure. Yeah, I was just wondering that because it was also 3.1.
Yeah, okay. Actually, now that I think about it, let me answer your question. Yes, it was a coincidence.
Okay. It's like,
But
that's weird
also,
that
no, it was not a coincidence.
yeah.
The problem
All
is
right.
both things are true, and I can't explain it to you.
Yeah, okay. All right, so then it would be multiply by a division bar from what we got, then 1 year on top, and 3.15 times 10 to the 7th seconds on the bottom.
I'm going to let it slide this time, but okay, fine.
What did I miss?
Well, I like units first and numbers second, but okay.
Okay, well, that was just, I knew all of them, I figured I'd just do it, but yeah, okay.
So what's the plot equal to?
That is, 1 second. That would be 1.5 over 3.15, which, right, because you cancel out the 10, the 2, 10 over 10 to the 7th.
Just give me the number.
Um,
Don't walk me through your spiritual journey. Just give me an answer.
sorry, I have to think about it. 0.47 years, or 0.48, I guess, if you're rounding.
Forest for the trees here.
0.48.
Half a year.
Oh, okay. Yeah, that makes sense. Okay.
Right? It's half a year. Four times the mass of the sun would change the period of our planet to half a year. How interesting. Now it's time to learn. Do you guys have all that? You got all that down?
1 second.
Sorry?
1 more second.
Sure. Just whoever you are in the background there, shout at me when you're done.
Okay, thank you.
All right. Now it's time for me to drop some knowledge on y'all, all right? Suppose you had been better at proportionality arguments. You'll remember that they tried claiming in this problem that the calculations are so simple that you don't need a calculator. Now, I don't know about you guys, but that didn't seem so simple to me, did it? Unless you were good at proportionality arguments. Look at it from the point of view of the kind of thing we did in the first problem. In part B, you had a distance that was the same, 1 AU, but a mass that was varying by a factor of 4 times. If you ignore the constants, you could write Newton's version of Kepler's third law as p squared is proportional to a cubed over the total mass. In this case, the a was only varying by a factor of 1, so it wasn't really varying at all, but the mass was varying by a factor of 4. And that tells us that p squared is proportional to 1/4. Now, if we square root both sides, we find that p is proportional to the square root of 1/4, and that's equal to 1/2. The new period is half the old period. And since the old period was 1 year, the new period is half a year. You could have done that in 3 lines with no calculators had you been able to wield the katana that is the proportionality symbol. This is a powerful samurai mathematical operator that only ninjas can use, okay? So it's worthwhile to learn how to use this. Professional scientists can evaluate very complex equations quickly and simply because they know how to wield this magic sword. All right, lesson over. Question 3 down the hatch. It's time to move on to question 57. Can I erase? I hope you took away that message there. That's an important message. Okay, before I have Valentina read us number 57. Wait, Valentina, did you read yet? Okay, cool. Before I have Valentina read us 57, I want to talk about 57 for a second. 57 is going to be a new variation of studying NK3. This problem is also another version of what we just did. But 57 involves using Newton's version of Kepler's third law solved for mass. Now, I'm going to skip the algebra exercise because no one's got the patience for it right now. But you can basically swap the total mass and the p squared to get a variation that looks like this. The total mass of my orbiting system, which is m1 plus m2, can be found by 4 pi squared a cubed over g p squared. This is still the same formula that we used in the last problem, but we've swapped the positions of the period and the mass, and we're now going to use the equation to find the mass of the orbiting system. If you guys are wondering about the kind of generic setup, because maybe I didn't do a good enough job explaining that, consider this crappy animation here. This is what NK3 is used for. It's used for 2 masses. They're in an orbit. They don't have to be circular, but we're going to pretend they're circular. The distance, whoops, that's an example of non-circular. The distance between them is A, so that's A, and the period is their period of revolution. All right? Let's see what's up in the chat log here. Oh, Yudi, I forgot to check on you to see if you got that last calculation, but maybe I'll check on you for this next one. Okay, Valentina, read us 57.
Using Newton's version of Kepler's third law. Calculate Earth's
Kepler's third law.
Calculate Earth's approximate mass from the fact that the moon orbits Earth every 27.3 days at an average distance of 384 million kilometers.
Is it million or is it 1,000?
1,000, sorry.
That's okay. So in other words, Valentina, these are what we call the givens, right? The givens. You guys will notice that when I solve a problem, I like to extract the givens with their units right onto the page. You should do the same thing. All right. Does anyone know how to get this going? How to kickstart this thing?
You change kilometers to meters.
Nori, that's an amazing idea. That's very important. Remember, class, A must be in meters and P must be in seconds for this to work. I was wondering if you were going to even notice that, but like I said, you guys are pretty good. Nori, set it up for me. Do the dimensional analysis with me. How do I start?
I'm trying to find the conversion of it.
Why don't you just get it going first? Like, what's the first step?
Converting it to meters?
Yeah, like what's the
Oh,
first step
oh.
in dimensional analysis?
Oh, write down what you're converting. So 384,000.
You're missing something.
And then you.
No. I don't like that. You said write down what you're converting 384,000. You forgot.
And it's unit.
That's right.
Sorry.
That part matters. That's the whole purpose of this is units. Okay. So that I treat
And
that.
then
Okay. Yep.
Sorry.
No, go
And
ahead.
then you
go
divide
ahead.
by a division bar.
Good. That's step 2.
And then you write down the units that you're converting. So I would assume that kilometers would be at the bottom and meters would be at the top.
Very good.
And I think it was 1,000 for meters. So 1 would be at the bottom and 1,000 would be at the top.
Nice. See, sometimes if you just start setting it up, you'll remember the conversion. I think you should always just get that in place before you go hunting for your conversion factor. Okay, can you do this in your head? What should that be in your head?
It's going to be 384 times 10 to the 6th power.
Nice. And how do I say that in English?
384 million.
Very good. Okay, awesome. Our A is taken care of. Now, Nori also needed us to do MKS units. That means 27.3 days is not going to work for our period. Kim, I would like you to help me do the period conversion. If I might ask you that favor.
Yep. It's going to be 27.3 times.
Whoa. What did I just get on Nori about?
Oh, days, 27.3 days.
All right.
Times. And I just have to find a good conversion for that.
No, first you have to put your units in before you even look at
Okay. Well, it'd be seconds on top. Well, actually, in year on the bottom. Or days on the bottom, isn't it?
Yeah.
Yeah, days, sorry.
Do you know the number of seconds? Sometimes you don't have to look up a conversion factor, Kim. Sometimes you can just know a conversion factor. I'm guessing you don't know the number of seconds in a year. That's okay. I bet you would know I bet you do know the number of hours in a year, right?
Yeah, 24.
See, you said year, and now I'm saying year. Fuck. Okay. You don't know the number of seconds in a day.
Right.
But you do know the number of hours in a day, correct?
Right.
So we could do a couple of hops here. So help me with the number of hours in a day.
It's 24 hours in a day.
All right, so what should I do next?
Times, down at the bottom would be hours, and on the top would be seconds.
Do you know the number of seconds in an hour?
Not offhand.
Do you know the number of minutes in an hour?
60.
So why don't we go to minutes instead? 60 minutes.
60. Yeah.
What should I do next?
Then it'd be times 60.
Well, units
seconds.
First. Units first,
Okay.
number second.
Seconds and minutes on the bottom. And it's 60 on top, 1 on the bottom.
Good. So we didn't actually have to look up anything. We just had to do dimensional analysis, right?
Mm-hmm.
All right. So what do you get for your period then?
I have a question.
Sure.
Could I just do, like, instead of doing like the 3 division bars, could I just do like 24 hours over 1 day times like 3600 over 1? Could I
Yeah.
do that?
If you know the number of seconds in an hour is 3,600, I might have done that myself. In fact, I might have done 86,400 seconds in a day. You can do whatever you want, provided you know the conversion.
Okay.
Right? Seconds in a day. Sure, that would have been totally cool. Anyways, what's the answer here? 3 sig figs will work.
No, it's not. 98280? No.
Wait, that's robot speak. Also, I don't believe it.
No, I know. 27.3
Kim, clear it out and try
times-
again. 27.3 times
3
24
times-
times 60 times 60.
$2,358,720.
That's a little too many sig figs, and I want it in scientific notation. I want you to round to 3 sig figs, and I want it in scientific notation.
27.3 times 24 times 60.
I'm not complaining that your answer was
Times
wrong,
60.
Kim. I'm saying that you
Okay.
said it to me.
Oh, okay. Sorry. 2 times 10 to the 6.
I want 3 sig figs. There's 3 sig figs here.
Okay. All right, 235.
2.35. What's the number after 5?
All right, 36, sorry. 2.36 times 10.
I don't trust you. All right, wait. 27.3 times 24 times 3,600. Okay, yes, 2.36. Now I trust you. Times 10. To what power, Kim?
4?
No.
5.
Count with me.
Oh, I'm sorry, from decimal, yep. So it's 10 to the 6.
Thank you. And what are my units?
Seconds.
Good. Okay. You're learning. You're learning. Our A has good units. Our P has good units. Now we can actually solve the problem. Make sure you've got that written down because I need to erase this. I'm out of board space.
I forgot to say it when I read it, but that will be part 8 of 57.
I'm sorry, Valentina, one more time.
I forgot to say it when I read it, but that will be part 8 of the problem 57.
Correct. And you'll see that I kind of knew that, but good call. We want to keep track of that stuff. Yeah, in other words, let's hurry the F up because we got a lot to do, right, Valentina? All right, I'm ready to move on. Let me erase this. Okay. So in our problem, the total mass is the mass of the Earth plus the mass of the moon is 4 times pi squared times 384 million meters cubed divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared times P squared, 2.36 million seconds squared. All right. Why don't you all give that a shot without my help? I want to see if you can do that without my help. I'm gonna take away the fig newtons before I make a mistake. Jenna, just read it to me. I don't even feel like looking.
9.2 times 10 to the 13th. I'm sorry, 9.22 times
Dude,
10
you
to the
did the
13th.
same thing you did before. You hit square, but you forgot to hit equals. Hit equals. What'd you get now? Just hit equals.
I have a question.
Sure.
So in the last one, when we had like the
Square root.
root, yeah, we divided the bottom one even though it said times. Are we supposed to divide it also in this one?
Yep, you got to divide it every time.
So we're
Otherwise
dividing it always.
Yeah, because otherwise the calculator doesn't know it's supposed to be in the bottom, right? Your calculator doesn't have little eyeballs sticking out that can see that this is in the bottom of the equation.
That
By
makes
hitting
sense.
divide, you're
Okay.
telling the calculator, and by the way, dude, this is also in the bottom, right? If you hit times, it's going to think you want it up there. What did you get when you hit equals, Jenna?
Double check. Yeah, 9.18 times 10 to the 13th.
You forgot to hit equals. That's the same thing you got last time. Just hit equals.
Yeah, it won't do anything.
All right, so never mind. You just fucked up. Punch it in again. Wait, do I have to do this with, did anyone get the right answer?
Is it 5.73 times 10 to the 24th?
That's good. But 5 points, you know, let's just round it up. You got about 6 times 10 to the 24. What are your units?
Newton?
No,
No.
not newtons. Who am I talking to right now? I'm a little confused.
Yuri.
Oh, hi, Yudi. Yudi, look at all these units here. Let's cancel some out. What units cancel out here? Do you know how to do that, Yudi?
Not really.
Well, do you want to learn?
Yes, sir.
Okay. So this meter has to be cubed. I also see a meter cubed there. Can I cancel them?
So the meters, yeah.
Do you see anything else that cancels, Yudi?
Seconds?
This is seconds squared.
Okay.
How about over here?
It's seconds squared too,
Because
right?
it's also squared.
Okay.
So it looks like seconds squared on the bottom, on the top of the bottom, cancels with seconds squared on the bottom of the bottom. What do you have left
So it's
over?
kilograms?
That's right, because it's actually 1 over kilograms, and the bottom of the bottom is the top.
Okay.
That actually makes sense, Yudi, because we were calculating a mass, and we would expect masses to be measured in kilograms.
Okay.
There's just one last beef. This is the total mass of the system, mass of Earth plus the mass of the moon. But they wanted us to get the mass of Earth. So what are we supposed to do about the mass of the moon? Valentina, there was another part to this, wasn't there? There was another little tidbit. Oh, fudge. Homework. Chapter 4. Come on, come on, come on. Oh, a previous one used to have a little hint. I guess they took the hint out. They wanted us to find the mass of the Earth, but this is mass of Earth plus mass of the moon. The idea is that we can neglect the mass of the moon as insignificant because it's like 80 times less than the mass of Earth. So we basically argue that the mass of Earth plus the mass of the moon is still just the mass of Earth. And that's the answer to part A. Did anyone need me to go over this computation?
So is 6 times 10 to the 24th power, is that the answer?
If you say kilograms afterwards, that's the answer.
Okay,
Okay, yes.
sorry.
That's all right. I just 6 times 10 to the 24 means nothing. 6 times 10 to the 24 kilograms is a mass. That's how I think. That's how I want you to think. All right, want to try B? God, do I ever. All right, here we go. I'm erasing. Next time I'll go through the calculation because I bet there's going to be people watching at home that struggled with that. So Valentina, what do they want us to do for part B?
Calculate Jupiter's approximate mass from the fact that its moon, Io, orbits every 42.5 hours at an average distance of 422,000 kilometers.
Okay. This time I want to speed things up, okay? Let's start with our A. Our A is 422,000 kilometers. We have to convert that to meters using the same technique as last time. 1,000 meters per kilometer. What's the answer?
Oh,
Go ahead.
422 times 10 to the 6th.
Meters. All right. Period. 42.5 hours. Oops. Nori was all hot to trot on the number of seconds in an hour, so we'll take advice from her. 3,600 seconds per hour. 3 sig figs, what's that? 3 sig figs.
Said 3 sig figs?
Sure, they gave us 3 sig figs, so we'll stay consistent.
It would be 1.51 times 10 to the 5th power.
It's less than a million, so I really don't need scientific
Seconds.
So how about just 151,000? Did you round properly, Nori, or whoever was talking to me then?
Yeah, I rounded.
Wait a minute. I get 153,000 seconds. Is that what you said? Did I just write it wrong? All right, let's get the total mass. The mass of Jupiter plus the mass of Io. How does the mass of Io compare to Jupiter, class?
I would guess it's pretty insignificant.
Yeah. I mean, have you ever seen this thing? Not that anyone's in the mood for this right now, but. I mean, There's from the Galileo space mission, an up close shot of Io in comparison to Jupiter. Look, you can even see the shadow of the moon on Jupiter, 400,000 kilometers away. I'd say the mass of Io plus the mass of Jupiter is pretty much just the mass of Jupiter. All right. So we'll neglect that. And that's equal to 4 times pi squared times 422 million meters cubed divided by 7 times 10 to the negative 11 meters cubed per kilogram per second squared divided by 153,000 seconds squared. Okay. Sorry, that handwriting wasn't so hot there. Although you live students were able to successfully calculate this, I'm concerned that there might be people watching later who aren't as good as you. And so I'm going to do this one with you to make sure that everyone has the procedure. Four times pi squared times 422 exp6 shift x cubed divided by 7 exp negative 11 divided by 153,000 square key equals. Jenna, Ian, do you got it? All right.
Yeah, it's just dim.
What should I round my answer to then?
1.81 times 10 to the 27th. And
I'm just going to make it 2 times 10 to the 27. What are my units?
kilograms.
Nice. Marker overboard. And it fell in my milk crate. You bastard. You stupid bastard. Oh, wait. Oh, hey, this is cool. Look what he found in his pockets, Mr. Baggins. His marble earth. That's cool. Unfortunately, I can't find the marker. That thing just totally vanished. Huh. All right. Luckily, I've got 10,000 more. Kilograms. That is so weird. Guys, I need to clean my house and my life up because they're both a mess. Ugh. Okay, all right, let it go, let it go. You guys got that? I need to erase. I'm erasing. One last problem to go. Unfortunately, I decided to just give us a little taste of this because I didn't quite get to that formula today, and I apologize. Problem 58 has to do with something called the escape velocity. The formula is much easier than the previous two, so we're just going to kind of crank this out quick. The escape velocity is the speed that you need to blast off of a planet. The formula is 2 times big G times the mass of the planet divided by the radius of the planet, square root thereof, where MKS units apply. The mass is in kilograms, the radius is in meters. Let's just do part A quick and dirty, and I'll explain it next week. So, Kim, I can't remember who I asked here. Oh. Kim, do you have that up? I can't remember who I asked to read.
Yeah, I have it. The escape
right.
velocity. Calculate the escape velocity from each of the following using data as needed from Appendix E. A, the surface of Mars.
Okay. The mass of Mars, it's about 1/10 of Earth. So it's 6 times 10 to the 23rd kilograms. The radius of Mars is 3,400 kilometers. Ian, I bet you could convert that to meters in your head without even trying. Could you do that, Ian? Because you seem to be pretty good at this.
Converting that to meters, it would be 3.4 times 10 to the 6th meters.
Since Ian is so good, and since we're so sick of doing homework, we're just going to use Ian's conversion, and I'll trust that you could all do the dimensional analysis on your own. Hopefully, that trust is well placed. That means we could quickly calculate the escape velocity of Mars and be done by doing the square root of 2 times G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times the mass of Mars, 6 times 10 to the 23 kilograms, divided by the radius in meters, 3.4 million meters, and then hit equals and then square root. Go ahead and punch that up and get me an answer. I'll explain this next time because we're sort of out of time and patience, I'm guessing. What'd you get, Jenna? Just round it and read it. 2 sig figs.
All right. 5.0 times.
Hold on. Let me just stop you. Is your answer bigger than 1,000,000? Yes or no?
No, it's 1,000.
So let's just round it to 2 sig figs, but not put it in scientific notation.
Okay. 4,900. Oh geez. Someone have to take it away.
4,900 is close. I just want to see if I get that. I remember it being a little bit over 5,000. Your answer is approximately correct. Let me just double check it. Oh, yeah. Okay. If you're going to round to, all right, here's what happened. You're rounding to 2 sig figs, which means you're cutting between the 9 and the 7, correct, Jenna? Don't you have an obligation to increment the 9? That increments the 4 to 5. So the correct answer is 5,000. What are your units? See if you can figure that out. I'll be impressed.
Is it newtons?
Hmm?
Is it newtons?
No, newtons is a force. This is a velocity.
Seconds?
Seconds
Squared?
is seconds is a time. This is a velocity.
Oh, it would be meters per second squared?
Meters per second squared is an acceleration. This is a
Okay.
velocity.
You said that if it wasn't like over 1 million, then you would do it, but mine came out like a lot of numbers.
Did you
Is that
square
right?
root it? Did you square root it?
Okay.
No, I'm asking you a question. Did you square root it?
Oh, yeah, I did.
Then you did it wrong. Why don't you punch it again? Here. Let me punch with you, okay? 2
2 times 7
exp
negative 11 times 6
exp
23 divided by 3.4
exp 6.
6.
Then you hit
Then-
equals, sorry, equals. Then shift.
And then root it. Okay, it's like, yeah.
Ryan has attempted to balance his units. Let's see what Ryan did there. Ryan, you're getting close, but you're not there. I agree, Ryan, that meter cancels out with meters cubed to make meters squared. I agree that kilograms squared. And yes, Ryan, I do agree that that leaves you meters squared per second squared. But don't forget, Ryan, that the square root distributes to the units as well. And the square root of meters squared per second squared is,
Meters over seconds, meters per second.
which is the units of velocity in the MKS system. Correct. Bonus if you can tell me the answer in kilometers per second. How many kilometers per second is that?
Wouldn't that be just 5?
That's right. It's customary to express escape velocities in kilometers per second, but I'll explain that to you in our next class.
So you want it in kilometers per second?
I really want it in meters per second because that proves that you punched all of that in. The kilometers per second is a classy move. So the question is, do you want to be classy? Pinky's out. Then we put 5 kilometers per second as an extra classy flourish, okay? But I really want it in meters per second. Okay. You guys learned a lot today, and you did surprisingly well. An hour and a half is half an hour faster than I thought today's homework was going to go. You definitely did better than my 1020 class. Trust me on that. So congratulations. These calculations will definitely get easier and faster as we go forward. Next time, more fun, okay? Please turn these in, like, comment, and subscribe, and I'll see you guys on Monday. Next week is our last week before the exam. That's going to be an important week. Next Monday, we'll do a lab on something. Probably more problems with this. And then on Wednesday, instead of doing a homework, we're going to have a homework session where I give you practice problems for the test. That'll kind of grease up your gears before you go into it, all right? And we'll talk about the test next week and all that. So good luck, guys. Turn those homeworks in, and I'll see you guys on Monday, okay?
I have a question.
Sure, let me stop.
When is this?
Actually, go ahead.
I was just gonna say, when is this video gonna be uploaded? Because I think I missed a part.
As soon as I hit stop, the video begins to render. And that takes sometimes an hour, sometimes a little more than an hour. Once it's rendered, I then have to upload it to YouTube, and then YouTube has to render it. That takes sometimes a half an hour, sometimes more. So if everything goes right and I don't get distracted and forget to come back and upload it, which does happen sometimes, this video could be up as soon as 2 hours from now.
Okay.
If not, check the video from last year if you need it faster, okay?
Okay.
Okay,
Thanks.
all right.